during this afternoon in this room. Both speakers are recipients of the Frontier of Science Award. The first speaker is Xin Sun from Peking University. He will talk about 2D percolation, random triangulation, and Liouville quantum gravity. Let's welcome.
Thank you very much for coming to my talk. Today I will talk about two seemingly quite different probability models. One is two-dimensional percolation, and the other is Liouville quantum gravity, and I will describe some relation between these. So I will focus on the so-called side percolation on triangular lattice, and so by definition, the side percolation is the coloring of these hexagon lattice, and this hexagon padding is actually a realization of the triangular lattice. So we view every hexagon as a vertex, and if two hexagons are adjacent, we view them having edge. And then this is a so-called side percolation. And so we color every hexagon with color black or white with probability p independently. And in these models, so we are interested in macroscopic events that describe the connectivity property of the percolation. And here, so a typical event that we are interested in is something called crossing event. So here, given a Jordan domain is a simply connected domain with whose boundary is a Jordan curve. So, and then we consider a Jordan domain with 4 mark point. And then, so we say that there is a left to right crossing if I can find a wide path connecting, separating CD and AB. Okay, and if this happens, we say that there is a wide crossing. And then, given a Jordan domain and given the size of the hexagon lattice, we can consider this event, the probability of this event. Apparently, this will depends on the parameter p, which is the probability of the white color, and also depends on the hexagon lattice size and also the Jordan domain with a 4 mark point. And we are interested in the behavior when this delta tends to 0. And it is a classical result of Henry Keston that if p is bigger than 1/2, which means it's more likely to be white. And then he showed that this probability will always tend to 1, which means at the macroscopic level, you will see the white cluster dominate the picture, and you will always be able to find such a crossing. And then on the other hand, if p is smaller than 1/2, then the black color will dominate, and then you will all be able to find a black path from top to bottom, which will be blocking the left-right path. And in this case, this probability tends to 0. And the most interesting case is the so-called critical case, where p equal to 1/2. So in this case, Keston showed that this probability, it has a non-trivial subsequential limit. And later in physics, so physicists, they consider that this crossing probability, it not only it should also be conformal invariant, meaning suppose I have 2 different Jordan with 4 mark point. If related by a conformal map, then their crossing probability should be the same. The limiting probability should be the same, and this is a so-called conformal invariance. On the other, in other words, it means that this limiting crossing probability should only depend on the cross ratio between the 4 points. If we map the Jordan domain with 4 points to the rectangle, this crossing probability should be a function of this aspect ratio of the rectangle. And then a bit later, John Cardy, a physicist, he based on some non-rigorous consideration based on the so-called conformal field theory, Cardy was able to produce the exact formula in the case of a rectangle. And if you know how to map a Jordan domain with 4 mark point into a rectangle, this completely solves this crossing probability. And so Cardy's formula was proved in a famous work by Smirnov. And so he actually proved a stronger theorem. So what Smirnov proved is the following. So what he considered is given any Jordan domain with 3 mark point, So suppose I have a Jordan domain with 3 mark points. Then there is a unique conformal map that map this Jordan domain to a equilateral triangle. And I'm choosing this particular equilateral triangle, which is this hyperplane intersect the first quadrant of the free space. Then there's a unique conformal map, which map these 3 vertices to the 3 corners. And then, what Smirnov considered is these probabilities. So I first use a triangular lattice to approximate this Jordan domain, and then so he considered the probability that I can find a percolation wide path that separates AZ and BC. So this is depends on the percolation, the lattice size, and it also depends on the point Z. So I'm using this to denote it. And then you can also consider the other 2. These are the 2 other functions. And then Liouville defines a function on the Jordan domain. And then what Smirnov proved is that these 3 this strip of numbers putting together as a function of Z, this will converge to this Jordan to this conformal map. And in particular, if you set Z equal to D, so if you set Z equal to D, then this PCD is exactly given by phi omega D. Okay, and now if you set omega equal to this, then this will give you the Cardy formula. So because there is a explicit formula that tells you how to do a conformal map from the rectangle, from any rectangle to the equilateral triangle. And using that formula, this exactly gives the Cardy formula. So this is Smirnov's proof of the Cardy formula. And from our perspective, what Smirnov did is that he used percolation to find a approximation of the Riemann mapping theorem. And we call these kind of things discrete conformal embedding. And before Smirnov's work, there's actually a more famous example of the discrete conformal embedding, which is a so-called circle packing. And this is based on the following theorem. So suppose we have a triangulation of the sphere. A triangulation of the sphere is a way of gluing together topological triangles to form a topological sphere. And then, so circle packing theorem says that any triangulation can be represented as a tangency relation between circles. And then, Thurston used the circle packing theorem to form a proposal of the discrete conformal embedding. And the conjecture is following. So given this Jordan domain, and I use the triangular lattice to discretize the domain, then I can view this triangulation of the sphere by view the outside of the domain as a single vertex. And then I can imagine that I can draw a edge between infinity every boundary vertices. Then this is the triangulation of the sphere. So now I can apply this circle packing theorem to visualize it as a circle packing of the sphere, and then this infinity becomes this outside circle, and then all the other vertices become the inner circles, and then so this form a map between every circle to every circle in this Jordan domain to a circle here. And then what the Thurston conjecture is that if you shrink a lattice on the left-hand side, then this will converge to the conformal map between this Jordan domain to this unit disk. And this was proved by Holden and Sullivan. Okay, so as I mentioned, similar to the theorem of Holden and Sullivan for circle packing, Smirnov's proof of the Cardy formula, it also provides a discrete conformal embedding based on percolation. And we call it Cardy-Smirnov embedding. And so the result that, so the paper that I wrote with Nina Holden that win this award is the following result. So what we are interested in is rather than consider a regular triangular lattice, so we consider a arbitrary triangulation of a disk, and then so actually for any triangulation of a disk with 3 boundary mark points, we can consider the percolation on this graph, and then using these numbers here, using this PAZ and PBZ and PCZ, we can use it to embed this triangulation to this equilateral triangle. And then the question we are interested in is as the size of the triangulation goes to infinity, suppose I uniformly choose the triangulation of a large polygon with 3 boundary mark points. If the size of this triangulation tends to infinity, what's the limiting geometry of this random triangulation? This is the question we're trying to understand. And what we showed is that okay, so suppose we have a triangulation, then it naturally induces a random metric, which is just given by the graph metric on the triangulation. For example, if you look at these 2 points, the distance between these 2 points is just equal to 2 because there are 2 edges, and the distance between these 2 points is equal to 1. So this naturally induces a random metric on this triangulation. And after you use the Cardy-Smirnov embedding to embed the triangulation into the equilateral triangle, this induces a random metric on the equilateral triangle. And then similarly, you can also induce a random area measure on equilateral triangle, which is given any open set. I just count how many number of points in this open set. So this defines a random metric and a random measure on this equilateral triangle. And the question is, as the size of the triangulation goes to infinity, what's the limiting geometry? And what we showed is that under this Cardy-Smirnov embedding, this random geometry this random geometry defined on the equilateral triangle induced by the triangulation, it converges to some continuous random geometry defined on the equilateral triangle. And this limiting geometry is also called Liouville quantum gravity. And in the next couple of slides, I will explain what's the definition of the Liouville quantum gravity. Okay, so Liouville quantum gravity is a theory of random surface originated from the study of string theory in 1980s. So before I go to random surface, let me first explain the classical story for random path. So we know that if we want to sample a canonical random path in probability, there are usually 2 ways. One way is using the so-called skinny limit. So for example, if I want to sample Brownian motion, I can use the skinny limit of a simple random walk. This is based on the central limit theorem. And this is a particular variant of Brownian motion, which is called the Brownian bridge. This is the Brownian motion condition on the event that at time 1, it's equal to 0. And another way of sampling this Brownian bridge path is using this Fourier series. So suppose we consider this Fourier series where the Fourier coefficients are given by IID standard Gaussian, then it can be shown that this random Fourier series, it converges almost surely in this uniform topology, which means I will get a random continuous function at the end. And you can show that this limiting function is also equal to the law of the skinny limit of simple random walk if you condition on the ending point at 1 equal to 0. So these 2 ways are 2 different ways of sampling this Brownian bridge. And in the last 15 years or so, a similar story has been carried out for random surface. So let me first give the discrete side. So instead of consider the random path, we can now consider a uniformly sampled triangulation of size n. So here by size, I just mean the number of triangles. So I just consider a uniformly chosen way of gluing together n triangles into a topological sphere. And there are only finite many of such possibilities. I uniformly choose one of them. And then I can view this as some metric measure space by just view this as a piecewise linear manifold, by viewing every triangle as an equilateral triangle, then this will become a Riemann manifold. And then, so in the space, so the space of metric measure space, there's a natural topology on this, which is the so-called Gromov-Hausdorff-Brockhoff topology. And then it's a landmark result independently by Legault and Mirmont. They say that this Mn viewed as a random metric measure space, this under some proper scaling, it will converge in this natural topology in the whole space of metric measure spaces. This will have a limiting object. And the limiting metric measure space, the topology is almost surely a sphere. So they call this Brownian sphere. And on the other hand, although the topology is always a sphere, they can also show that the Hausdorff dimension of this object, of this metric measure space, is always equal to 4, which means it is a very rough surface. It's a topological sphere, but it's not smooth. And there are similar stories for Brownian disk, which means I consider a very large polygon and a uniformly sampled triangulation of a large polygon. If you scale the boundary length of the polygon and the number of triangles in a appropriate way, then they will be limiting metric measure space, which is homomorphic to a disk, and that is called a Brownian disk. And the local geometry of the Brownian sphere and Brownian disk, they are the same. Okay, and then now I want to describe the other way of describing these Brownian surfaces, which is the so-called Liouville quantum gravity. And the basic input of Liouville quantum gravity is the so-called Gaussian free field. And the Gaussian free field itself is a two-dimensional analog of the Brownian bridge that we saw in a couple of slides ago. So given any Riemann manifold, so in my lecture, the Riemann manifold will be two-dimensional. And then, so the Gaussian free field is similar to the Brownian bridge, is also a random Fourier series. So the Fourier coefficient is also this IID Gaussian, and the Fourier modes are given by the non-constant eigenfunctions of the Laplacian on this Riemann manifold. And then, so since we are in two dimension, you can actually show that this random Fourier series, it does not converge as a continuous function, but it converges in some negatively indexed Sobolev space. And the covariance of this Gaussian random function, the covariance is equal to the green function of the Laplacian, which has a logarithmic divergence in the diagonal. And this means that this is not pointwise defined. If you naively set y equal to x and try to compute the variance will be equal to infinity. It means it's not pointwise defined. And if you really want to simulate this random function, you can only simulate some modifier of this function. So for example, you can consider a circle average. So just fix a small epsilon. And then for every point, you can consider the circle average of radius epsilon of this function. And then this will be a random continuous function. And this is a plot of this function. And as epsilon tends to 0, this will be rougher and rougher. Eventually become something not well defined as a pointwise function. And formally speaking, the Liouville quantum gravity is a random geometry defined on domains which are induced by exponentials of Gaussian free field. More precisely, so let's consider some Gaussian free field on the Planar domain. Let's forget about the word variant for now. So consider phi as a Gaussian free field on some Planar domain. And then, so the Liouville quantum gravity is a way of defining some random metric and random measures on this domain D. And the random measure is defined in the following way. So formally speaking, it is a Lebesgue area weighted by this density, e to the gamma phi, where phi is some real parameter. And then, so since since the Gaussian free field is not pointwise defined, the way to make it rigorous is first we need to do this modification procedure, and then we do some normalization. And it's not hard to compute that the right normalization has to be this power. And then as epsilon to 0, it can be shown that when gamma is between 0 and 2, this limit, this will converge in the weak star topology to some random area measure on the domain D. And so formally speaking, this is some measure which is absolutely continuous with respect to the big measure. But since phi is very singular, this limiting measure is actually singular with respect to the big measure. But this is a well-defined measure, random measure on this domain D. So similarly, if this domain has a non-trivial boundary, then we can use a similar procedure, this regularization and normalization procedure, to define a notional boundary length on this boundary of D. And so we can also use similar philosophy to define a random metric on this domain by doing this similar procedure. But this is technically much more difficult. And this was only achieved much later in these two works. But conceptually, they are of a similar flavor, which is we first regularize the field, and after that, so this phi epsilon is a well-defined random continuous function, and then we can consider these geometric quantities. And then by taking some normalized limit, we define some limiting random geometric object, namely the random area and the random metric. And so for our talk, I'll just say that Gaussian Liouville quantum gravity is a one-parameter family of random geometry defined on planar domains, where formally it looks like this. Okay. And it can be well-defined. And so now let me explain what do I mean by a variant of GFF. So we can see that if phi is not just a Gaussian free field, but a Gaussian free field plus a continuous function, then all of these procedures, they can be carried out equally well. Because whether this is well-defined, it only depends on the local roughness of the random function. It doesn't depend on the fact that the Gaussian free field is a Gaussian function. It can be any arbitrary, so the global law of this random function can be arbitrary, as long as the local roughness is comparable to this Gaussian free field. So because of this, I have the liberty of just to consider anything which locally look like Gaussian free field. For example, the Brownian bridge is not exactly Brownian motion, but their regularity look the same. And this will be important later if we want to relate to the Brownian surface. Okay, so now I'm ready to explain the precise statement of the theorem that I proved with Nina Holden. So first, there's this breakthrough work by Jason Miller and Scott Sheffield. They construct an explicit variant of the Gaussian free field phi on this equilateral triangle. And then if you plug in this random metric, random area measure, and the random boundary length defined from this Liouville quantum gravity from the last slides using their variant. And if you set the gamma parameter between 0 and 2 to this particular number. So now this is a well-defined, so there is a well-defined variant of Gaussian free field, and this number gamma equals square root of 1/3. And if you using this to define this Liouville quantum gravity, random area, random metric, and random length, then they showed that this will be isometric to the Brownian disk, which means if you view this as a metric measure space, the metric measure space is the same as the Brownian disk, which is the scaling limit, which is the scaling limit of the uniformly sampled triangulation. And the same statement holds if you replace this Jordan domain by any similarly connected Jordan domain. And if you replace this Brownian disk by a Brownian sphere, then you can just replace it by any remaining manifold with a spherical topology. You can, for any remaining manifold with a spherical topology, you can always find the variant of GFF phi on this, so that this Liouville quantum gravity, random metric, and random measure pair is isometric to the Brownian sphere. So this is this established the link between the Brownian surfaces coming from the scaling limit of random triangulation and the Liouville quantum gravity. And okay, so with this in mind, so what Nina Holden and I proved is just, so suppose I consider the pre-limit of the Brownian disk, which is a very large uniformly sampled triangulation polygon. If I use, with 3 boundary mark points, if I use the Cardy-Smirnov embedding to draw this triangulation in this equilateral triangle, and then this naturally induced random metric and random measure on the equilateral triangle induced by this random triangulation, it will converge in the scaling limit to this metric. and measure, constructed by Miller and Sheffield. And in another word, it says that although this Brownian disk is a very rough surface, it's a topological disk, but the Hausdorff dimension equal to 4. Although it's a very rough surface, you don't expect there is a uniformization theorem, but we can think of this Liouville quantum gravity as a uniformization of the Brownian disk. So because the Cardy-Smirnov embedding is a discretization of the conformal map. So this is the theorem that we proved. And I should say that our theorem is built on several previous works with many other joint authors. Okay, and our result is a special case of this very general conjecture in random planar geometry, which drive the field. So the general conjecture in our is the following. So there are various notions of discrete conformal embeddings. As I mentioned, another very natural one is the circle packing. So this is we first sample some. So we first have a uniformly sampled triangulation and of a large polygon, and I use circle packing to draw it on this plane. And then we can see that each different circles represent different vertices, and this also induces some like a random metric and a random measure on the unit disk. And we can say just the distance between the two different circles is just given by the graph distance on the triangulation, and the area measure is just every circle, although they are not the same size in the Euclidean measure, they are of the same area measure under this random area. And so the general conjecture, this meta-conjecture, is that okay, so there are various notions of discrete conformal embedding, but as long as I use some uniformly sampled triangulation, or maybe I change it to uniform quadrangulation, which is replacing the triangle by quadrangles, or like even other class of maps. As long as I use some uniform measure on a certain natural class of random planar maps, and then under this discrete conformal embedding, this discrete geometry, it always converges to this continuum geometry defined in terms of the Liouville quantum gravity, which is the one given by here. And this is a general conjecture. And so the case, so this circle packing case is still open. Although it's a very natural statement, but this is still open. And I should say that even until now, the only proved case of this conjecture is still the my paper with Nina Holden, and under this particular Cardy-Smirnov embedding. And I think, I mean, so we never wrote the paper, but I think with some quite technical work, it's possible to replace the triangular condition by other maps. So in our original paper, we consider the triangulation, but I think that condition can be loose. But we have to use this particular embedding, which is coming from Smirnov's proof of Cardy formula. And the circle packing case is still open. There's another very natural conformal embedding, which is I just view this. So another very natural one is I just view every triangle as an equilateral triangle, and this becomes a Riemannian manifold. And for any like Riemannian manifold, there's a uniformization theorem that can be used to conformally map it to a unit disk or a unit sphere. And then it's also natural to imagine that under that natural embedding, this conjecture would hold. But that is also open. So this is the only case which is proved. And there are certain weaker notion of convergence under which other type of convergence are proved. And also, if you change, okay, so suppose you remember, so when I define this Liouville quantum gravity measurement measures, this parameter gamma, it can be varied between 0 and 2. And if you want to get other values of gamma, you need to change this uniform by some non-uniform measures. So there's so for every gamma between 0 and 2, there is a natural family of non-uniform random planar maps that the scaling limit is given by is the Liouville quantum gravity. But in my talk, I will just focus on this uniform case. Okay, so so now I have already finished presenting our result. So now in the rest of my talk, I will just give some idea of why probabilists are interested in this thing called the Liouville quantum gravity. Okay, so and let me see. So I think I was trying to. All right. So there's one more important point that I forgot to mention, which is so how this variance of Gaussian free field is defined. So as I mentioned in this original statement of Nina and Sheffield, they were just saying that they can construct some variant of Gaussian free field that once you plug in this field in this Liouville quantum gravity construction, this will be equal to the Brownian disk. And then if you change this remaining manifold by any manifold, you can always assign some random, some variant of Gaussian free field to produce this Brownian surface. But later it was understood that the way to produce this field is actually given by some conformal field theory. And the conformal field theory is the so-called Liouville conformal field theory. And I will skip the discussion of Liouville conformal field theory for now, but I will first explain so why at first place probabilists are interested in study random the Liouville quantum gravity. And so there are two natural motivations, and one natural motivation is that it is just very natural to study random surface. So so the Brownian motion is the most canonical random path, and it is equally natural to consider what's the most canonical random surface. And this is one motivation to study this Liouville quantum gravity. But there's another motivation which is coming from statistical physics, and this is a so-called KPZ relation. So in statistical physics, we usually are interested in these kind of problems. So this is a problem which is suppose I have a lattice of size n square, and so I'm interested in how large is the size of the boundary connecting cluster. So by boundary connecting cluster, I mean so this very big purple cluster. So I say that a vertex is on a boundary connecting cluster if I can find this a pink path connecting to the boundary. So this this whole thing is the so-called boundary connecting cluster. And a typical question in statistical physics, for example, in the percolation model, is to ask what is the size of this boundary connecting cluster? And the answer turns out to be the typical size is of this order, is n to the 91 over 48. And this is of natural interest in 2D statistical physics. And on the other hand, this is actually something not very easy to derive. I mean, so on one hand, this is a very natural combinatorial problem, but it's not easy to derive. And so the KBZ relation is one way of deriving such exponents. So the idea is the following. So the idea is that rather than consider this original problem, I change the problem to a random lattice. So I change this regular triangular lattice into this random triangulation. So I consider a random triangulation of size n square, which means I will put n vertices on the boundary and n square vertices on the bulk, similar to a Euclidean case. And then I can also consider a percolation here. And then now I ask how large is the boundary connecting cluster, which is this cluster, just these blue vertices and together with these things. And it happened to be the case that once you change the combinatorial problem on the triangular lattice, on this random triangulation, this counting problem becomes much simpler. It becomes something more tractable because of the freedom of also changing the background. And then it's actually easier to compute the corresponding number here. And I will not, so I didn't give the precise number, but I will just call this a quantum exponent. Because so here, so on the, so this regular lattice, it would corresponding to the flat geometry, the Euclidean geometry. So I would call this exponent the Euclidean exponent for this model. And this, when I allow this triangle lattice to be random, I will imagine this is a random surface, and this is a model for quantum gravity. So I will call this number the quantum exponent. And if you only have this is like a cheating, because a priori, nobody would be interested in percolation on this random lattice. They would be more interested in the percolation on regular lattice. So, and now I change the lattice, I solve the problem, but I solve the simpler problem, which is less interesting. And the magical thing of the KBZ relation is it is an explicit quadratic relation between this quantum exponent and the original exponent that we are interested in. And then once we plug in this formula, it pop out this 91 over 48. So this is a physical way of deriving this exponent using the so-called KBZ relation. And the KBZ relation was first proposed in the conformal field theory approach to this Liouville quantum gravity, and it is let's say verified in physics using enumeration techniques in random parameter maps, such as random geometry, such as random matrix, and so on. And so once physicists convinced this is the right method, it provides a powerful framework to study random fractals. And one of the most famous application historically of this KBZ relation is the so-called Mandelbrot conjecture. So Mandelbrot conjecture says that if I run Brownian motion up to some time, and I consider what is the maybe I can formulate it in terms of simple random walk. So I run a simple random walk up to a certain time, and then let's say I run a simple random walk in a box of size n by n, and then I run a simple random walk until it hits the boundary of the box, and then I ask how many vertices are there on the boundary of this trajectory, and the answer is n to the 4/3. And if you replace simple random walk by planar Brownian motion, the statement becomes the frontier of the planar Brownian motion has fractal dimension 4/3. But it is, using the relation between simple random walk and Brownian motion, this can also be viewed as a very simply stated combinatorial problem of random walk, which is just counting how many vertices are there on this boundary. This is very similar in nature to the previous problem we see of counting how many vertices are there in this boundary Canonical class of percolation. And this also appeared to be a super difficult problem. It was proposed by Mandelbrot in 1982, and without a very convincing argument. And I think the first physically very convincing argument is provided by Bertrand-Duplantier using the KBZ relation, which means, so he first considered the same problem of if I run a simple random walk on a random triangulation, basically means that so I consider a simple random walk on this graph until the simple random walk hit the boundary, and I count how many vertices are there along the boundary. And this turns out to be a simpler problem. And then once he figured out that corresponding quantum exponent, once you plug into the KBZ relation, he finds it's 4/3. And this is the first convincing argument for this Mandelbrot conjecture. And later, this Mandelbrot conjecture was rigorously proved using some machinery called Schramm-Loven evolution by Lawler Schramm-Werner. And this proof has nothing to do with the original derivation by Duplantier. But I think because of this very intriguing derivation, probabilists such as Aldai Schramm, they become very interested in understanding the mathematics behind this relation, which is quantum gravity. And so after about 10 years, Duplantier and Sheffield, they proposed the rigorous framework of Liouville quantum gravity, which is the random geometry induced by the expansion of Gaussian free field. And they proved the first rigorous version of the KBZ relation. Okay, so so to end my talk, I will just present a recent application of the KBZ relation by myself and some other authors. To motivate that, so we consider the so-called percolation arm exponent. So remember, so I was explaining that the KBZ relation can be used to derive this statement. And another equivalent way of stating this is suppose so given a bulk point in the percolation lattice, what is the probability that I can find some single color path connecting from this interior point to the boundary? And this is certainly decay to zero. And the question is, what is the decay rate? And so basically, there is a path connecting from here to the boundary. It's the same as saying that this point is on the boundary canyon cluster. And because of this, so saying that the boundary canyon cluster have size, roughly speaking, n to the 91 over 48, it's the same as saying that this event decays as rate n to the minus 5 over 48. And this exponent, 5 over 48, is the so-called one-arm exponent for percolation. And again, so this exponent was originally known in physics using non-rigorous method, such as conformal field theory or quantum gravity. But it was later rigorously proved using the so-called SLD, which is the same thing that people use to prove this Mandelbrot conjecture. They derived that this exponent is 4 over 48, 5 over 48. And okay, so I will not say too much about the Schramm-Lohner evolution, but I will just say that the starting point of the revolution in the random geometry is based on this observation by Schramm. So what he realized is that in many statistical physics models, such as percolation, so the model can be encoded by looking at the interface between the black and white clusters. And then he realized that if you assume the conformal invariance of these models, then the random interface, they can be the scaling limit of this random interface, they can be they will converge to a single parameter family of random curve, so-called SLD. And there is a kappa parameter, and it is proved by Smirnov that the percolation will convert to SLD6, and there are other famous models convert to other parameters. And so based on this, basically any large-scale problem about percolation, it can be translated into a problem of SLD6. And this is how this thing is derived. So there's a natural SLD statement that once we prove, then we will derive this exponent. Okay, so similar to the one-arm exponent, it's equally natural to ask some more to allow more arms. For example, so this is an example of the so-called polychromatic four-arm event, which means I consider an interior point and I ask what's the probability that I have 4 different paths all to the boundary. I have 4 disjoint paths to the boundary, and so I require these 4 arms to use both colors of black and white, and this is a so-called polychromatic arm event. And depends on arm k, I denote this exponent to be alpha k, and also using this using certain non-rigorous physics argument, it's possible to predict that this alpha k equal to this, and this is also rigorously proved using the SLD techniques. And it's equally natural to just allow the disjoint arms to have the same color. And this is a so-called monochromatic arm event. And the most famous one is the so-called backbone exponent, which is the case k equal to 2. And which means I ask the decaying rate of the probability that from an interior point, I have 2 disjoint arms to the boundary. And surprisingly, although this is like a seemingly like equally natural to the polychromatic ones and the one exponent, the value of this exponent was actually open for a long time. There was no physical conjecture for this value before the introduction of SLD, And even after SLE, the traditional SLE method solving the one-arm exponent and polychromatic arm exponent does not give an answer to this question. And this is the final application of the KPZ relation that I want to present. So last year, so with co-authors, I proved that this backbone exponent is the unique solution to this very simple equation. And the numerical value is equal to this. And if you use some not very hard transcendental number theory, it can be shown that this number is actually transcendental. And this was a bit surprising because all of the previously known population exponents, they are rational numbers. And there are some reason to think that this backbone exponent should also be a rational number. And actually some physicists, some mathematicians and physicists, they believe that this Cassi, this exponent should be the closest rational number, closest to this numerical value. So initially the conjecture was that, the initial conjecture was that Cassi would be equal to the one-arm exponent plus the two-arm exponent of the polychromatic case, which would be equal to 4 over 48 plus 1/4, which is this. And this is equal to, so the first two digits actually agree with the correct answer, and the early simulation only simulate correctly the first two digits, and then people conjecture that this would be the right answer, and there must be a very beautiful argument showing that this is the case. There should be some combinatorial argument relating the backbone exponent to the one-arm and the polychromatic two-arm exponent, which will give you this. And but then later some physicists they have some pretty so they have some sharper numerical estimates, and they were able to estimate the first four digits, and they realized that this was not correct. But even after that physics paper was published, okay, my time is probably up. But so even after the physics paper was published, there are still some theoretical physicists. They were saying that that numerical because this must be correct, and our result shows that their simulation is correct, and this is indeed a transcendental number. So my time is up, and I don't have time to go to the details, but I would just say that the proof relies on the coupling. So the statement is purely about SLE because of the connection between population and SLE. But the way we derive it is using the coupling between SLE and this Liouville quantum gravity, which means I'm using quantum gravity to derive some lattice model result. And I would view this as the application of this idea of KBZ relation. But it is still a bit more advanced than these original things did in physics, because otherwise the physicists would be able to derive it without my help. And the new thing that we rely on is this conformal field theory behind this Liouville quantum gravity, the slide that I skipped. I will stop here. Thank you. You mean you always want to express? I mean, I think you can always express certain scaling exponents using this quantum gravity type things. Yes, that's how we eventually derive it. Yeah, that's how we eventually do. I mean, so there are two steps. I mean, so this Bible, I mean, because of the relation between percolation SLE, it's possible to represent the backbone exponent using some SLE quantity. And Greg, who is in the audience, with Nina Holden and Alder Schramm, they have some other paper which relate this backbone exponent to some SLE quantity. But there are actually many ways to encode this backbone exponent, and there's a particular one which is very suitable to this approach, to this CFT approach. So basically, so the paper have two steps. One is how to find the right way of encoding this backbone exponent in terms of SLE, and then how to use CFT things to solve this problem. Yeah, it's one part of this. Yeah.
Okay, due to the time, if you still have any question, you can talk with our speaker afterwards. Okay, so let's thank our speaker again.
Thank you.